Hey everyone, this is Paul with GoEngineer and welcome to the GoEngineer YouTube channel. In this video, we are going to take a detailed look at the workflow involving interactive feature recognition using SOLIDWORKS CAM Professional and CAMWorks 2-axis turning. This video is for anyone interested in programming 2-axis turning, and it also builds upon what was covered in my previous tutorial, 2-axis turning basics using automatic feature recognition. The same principles and fundamentals also applies to everyone using SOLIDWORKS CAM Professional and CAMWorks 2-axis turning. So let's get started. As before, we're going to generate NC code from this example SOLIDWORKS part file, but using a different approach. Let's take a look at what's involved. Using a SOLIDWORKS reference feature to prepare the part so that it complements the CAM-specific machine environment. Define the stock, which is the material type, size, and shape from which the part will be machined from. Review how we are going to program this part and think about what features, internal and external, is appropriate for each setup. Then create applicable turn setups using interactive feature recognition. And once all machinable features have been identified, generate that information into operation plans. This contains how each machinable feature is to be used and how the NC code will output. And from these operation plans, generate toolpath to see how each cutting tool is used for that specific operation. Next, we will review our work by using the verification tools, step through toolpath, and simulate toolpath. And finally, post-process, review, and if necessary, edit the NC code. Part programming and machining is a subjective matter. In addition to a person's background experience and personal preferences, external factors such as the availability of their favorite machining center, what kind of cutting tools, work holding fixtures, or how the part is going to be held as it's machined are all valid considerations. With this given part, I'm going to create two turn setups, as I have machinable features on both sides of this flange feature. To properly establish the CAM environment, the first thing I'm going to do is create a dedicated SOLIDWORKS coordinate system from this location of the part. I'll create a new sketch using a vertical line from the SOLIDWORKS sketch origin of this part using the customized mouse gestures. SOLIDWORKS mouse gestures are invoked by holding down the right mouse button and simultaneously moving the computer mouse ever so slightly to display this functionality. Next, ensure the appropriate sketch relations are added to fully define this sketch entity. This vertical line will be used to help orientate our SOLIDWORKS coordinate system. Once done, exit this active sketch by using the shortcut key to activate the confirmation dialog. Pressing the spacebar displays the SOLIDWORKS orientation view dialog, as it helps visualize the orientation of the SOLIDWORKS coordinate system. Then press the S key for shortcut commands available at the feature level. From the cascading menu, select Coordinate System. Within the Property Manager, we are only concerned with three selections: the center point or SOLIDWORKS origin of our part, the gray vertical line that establishes the x-axis, and finally, an entity, whether it is a planar face or reference plane that establishes the normal to direction for the z-axis. Axis colors, green, red, and blue help determine proper orientation, and it is the same colors used for the SOLIDWORKS reference triad. Toggle the reverse direction icons to achieve the desired result as shown in the SOLIDWORKS display area. Once done, right-click, then select the green checkmark or OK, as this will confirm these existing settings. Next, I'll switch over to the CAM environment by displaying the CAM Feature Tree tab and the CAM Command Manager. The CW tab, or for people using SOLIDWORKS CAM Professional, the icon highlighted in red will be displayed. Defining the machine environment is accomplished by clicking on the Define Machine icon up in the Command Manager. Another method that I personally use is to right-click on the machine node, then left-click on Edit Definition. Working methodically from left to right, I'll start with the Machine tab. For those of you who are using SOLIDWORKS CAM Professional, there are slight differences in available selections, but overall, what is needed for this part is Turn Single Turret, Inch under Turn Machines. Once this selection is made, notice how the machine environment changes on the CAM feature tree as it now complements turn machining. You may encounter this message indicating that a lathe post-processor file is needed. Acknowledge the message by clicking on OK, as I will address this soon. On the Tool Crib tab, we will be selecting Default Tool Crib to Rear Inch as the active tool crib and its default cutting tools to be used for machining. Click the Select button. The Post-Processor tab displays all available default post-processors, and its main job is to parse our CAM information into NC code. This NC code is then used to control operations of the CNC lathe. If you recall moments ago, a message indicating that a lathe post-processor file is needed and the field Active Post-Processor is not found is now blank. To populate this blank field, click on Browse, then choose the given file path and actual post-processor to be used. For this application, I will be using the Haas ST20 post-processor. Once highlighted, again, click on the Select button as this selection assigns it as the active post-processor from the available file location listing. The Posting tab displays any existing logic from the selected post-processor, and as I do not have any special conditions, I will use these default values. The Setup tab in 2-axis turning allows us to define a new user-defined coordinate system and assigns it as the fixture coordinate system for the main spindle. Since we previously created a SOLIDWORKS coordinate system, I'm going to specify this under the Method field and choose it from the available Coordinate Systems field or from the SOLIDWORKS Flyout Feature Manager tree. The SOLIDWORKS display area will update based on the selections made, and select the green checkmark to accept these settings. Although I can assign dedicated work offset value here, I'm actually going to assign it using a different method later on. Other settings below, such as spindle direction, turn feature section plane, and turn feature display pane, can be adjusted. For this application, these default settings will be fine. The last tab to define is Chuck Fixture. By clicking on the Edit button, I am using the active default 6-inch 2-step chuck from the name field within the Chuck Management group box. Then select the green check mark to confirm these settings. As with any SOLIDWORKS model display, we can choose what type of display is shown from the pull-down menu for our chuck fixture. For this application, let's choose Transparent. Select OK to confirm our settings and exit the Define Machine page. The Stock Manager in the 2-axis turning environment is the material from which the part will be machined from. After clicking on the Stock Manager button from the Command Manager, the Property Manager contains default values which defines the current stock. The CAM-specific materials used for feed and speed calculations utilizes a different database from the SOLIDWORKS materials library. For this application, I'll be using the material grade A10 tool steel from the pull-down menu. The bar stock that I'm using is 4¼ inches outside diameter, and I want to machine an additional 100,000ths of an inch of material from the front face of this part. I also want to have enough material for my chuck jaws to hold on to, yet have enough clearance for my parting tool. The value of 1.15 of an inch for excess length on the backside will be just fine. As I'm specifying these values from the offset parameters group box, the transparent stock image updates in relationship to the actual part over in the display area. Within the bar stock parameters group box, the overall size of the stock is numerically displayed. In this example, I can saw cut my bar stock to an overall length of 5.75 inches. I'm satisfied with what I currently have. Now it's a matter of selecting OK to confirm these settings. The next step when programming interactively is creating a turn setup. This will eventually contain important information such as part orientation from its assigned work coordinate system, machinable turn features, and its associated strategies. Right-click on the coordinate system node, then left-click Turn Setup. Verify that the assigned fixture coordinate system is located and orientated in the correct position. After selecting the green checkmark, a Turn Setup 1 is now created within the CAM feature tree environment. The first thing I want to do is machine the front face of this part. It is a process of creating a turn feature by right-clicking on Turn Setup 1 and left-clicking on Turn Feature from the cascading menu. From the Feature Group Box pull-down menu, I'll select Face Feature as my type of feature using the Rough and Finish strategy. The display area will highlight the machinable profile of the part. To make filter selection easier within this area, I'm going to look at this part normal to the machine view, which coincidentally is the same orientation as my SOLIDWORKS front view, and zoom in a little bit closer in this area. Next to the active cursor is a pink funnel-shaped icon, which is the filter selection. This indicates what type of geometry will be selected for this face feature. After clicking on the left edge/face, the selected entities will now display the items picked in this field. Right-click anywhere within the blank display area, then left-click OK to confirm these settings. The CAM feature tree will now display a face feature with Rough and Finish strategy in blue text color. The next feature type I would like to create is using a slightly different workflow, but still arriving at the same destination. With Turn Setup 1 highlighted, go up to the CAM Command Manager, and from the Feature pull-down menu, select Turn Feature. For this example, I'm choosing an ID feature type using the Rough Finish strategy. Looking normal to the machine view of this part, it's a matter of selecting the appropriate internal diameter profile geometry and have it populate in the Selected Entities field. After clicking on OK and returning back to the CAM feature tree, it now displays the additional ID feature with Rough Finish strategy in blue text color. You'll notice a methodical approach when creating interactive features. This is intentional, as this workflow minimizes any questions and/or frustrations for this method of programming. In this next example, an OD feature with Rough Finish strategy is needed. Rather than choosing the OD profile entities, I'm actually selecting the faces, which is associated to the OD profile entities. As I look closer in detail at this external groove feature, It is intentional that I had skipped this area as I want to create an independent OD groove rectangular feature later on. Within the selected entities group box and highlighting join 1, you will now see numerical values display in the display area. This will give you the opportunity to either recognize the selected entities as is, as shown by the active chain radial button, or bypassing them by choosing the straight radial button from the Join Group box. After clicking on OK to confirm these settings and returning back to the CAM feature tree, I now have OD feature with rough finish strategy in blue text color. Speaking of that OD groove rectangular feature, I'm going to program this feature next. Once again, I'll reuse the same workflow of creating a turn feature by using the appropriate icon located on the CAM command manager. After making selections for the groove rectangular, OD feature type, and its rough finish strategy, I'm going to take advantage of using Windows box selection to select the profile geometry. In the Selected Entities group box, there's a checkbox below indicating Windows selection. When you check this box to make it active, you are now able to left-click, hold, and drag a Windows-style selection box over the geometry profiles in the display area. Right-click to bring up the In Context menu, and select OK to confirm these settings. I now have a groove rectangular OD feature with rough finish strategy in blue text color. The next machinable feature will be making use of the parting tool. For this item, right-click on Turn Setup 1, then left-click on Turn Feature to activate the Property Manager. So the choices for Cutoff Feature Type with Cutoff Strategy is selected. Over in the display area, choose the left edge/face of the part and verify the geometry selection populates in the Selected Entities field. Right-click to bring up the In Context menu and select OK to confirm these settings. I now have a cutoff feature with cutoff strategy in blue text color. The next step is to generate operation plan for all interactive machinable features by right-clicking on Turn Setup 1, and from the cascading menu, select Generate Operation Plan. After some flashing and dashing, the CAM operation tree is active, along with our single turn setup and the relevant operation plans from its machinable features underneath in blue. This contains information on how each machinable feature is to be machined and how the NC code will output. To actively view and edit the definition of our toolpath, the next step is to generate toolpath, as this will convert all of our operation plans from blue to black text colors. Once this process is done, you can hover over each active operation to see its corresponding toolpath in the SOLIDWORKS display area. Yellow warning markers typically indicate that the cutting tool used for this operation was not initially available from the selected tool crib. To satisfy the operation's requirements, SOLIDWORKS CAM Professional and CAMWorks selects the appropriate cutting tool, which complements this operation from the main tool library of the technology database. To clear this warning, right-click on the operation plan with the warning marker, navigate to what's wrong, then select Clear to acknowledge this warning. The same process is repeated for the other operation plan below. The next step for this part is to modify existing operations which affect the machined outside diameter. The strategy is to reuse a known machined feature from Turn Setup 1 so the part is running true when I chuck it up in preparation for Turn Setup 2. To get a better view of how much stock is machined, I'll look normal to the machined front view. Starting with Turn Rough 1, Right-click to expose the cascading menu, then left-click, Edit Definition. From the Operation Parameters dialog, click on Feature Options tab. Then input the value of 2.15 for the end length within the Features group box. Selecting Preview updates the graphical representation of toolpath geometry. This calculated value is the distance between the left face of the part to the flange face, plus the distance from the end of the part to the chuck jaws, plus thickness of the parting tool, the tool holder, and just enough clearance to cut the part from the remaining stock. Then clicking on OK confirms these new settings. For turn finish 1, I'll repeat the same workflow as in turn rough 1, and by selecting Preview. It updates the graphical representation of the tool geometry, then clicking on OK confirms these new settings. As best practice, Simulate Toolpath can be utilized for checking any unforeseen issues which may present itself with the given edits made. At this point, all looks good for now. For those of you who want to use a dedicated work coordinate value, it's a matter of editing the operation setup parameters of turn setup 1, clicking on the Offset tab, and keying in the value of 54 for the work coordinate. With turn setup 1 machinable features, strategies, operations, and toolpaths completed, I'm now focusing my attention of what to program next for the remaining area of this part from the CAM feature tree. Part viewing from a machining perspective is made easier by looking normal to the part with the assigned SOLIDWORKS coordinate system from the left side. From the CAM Command Manager, I'm going to create a new turn setup using the existing work coordinate system from turn setup 1. The main difference is that I am reversing the setup direction as indicated by the checkbox. A message indicating the suggested use of a main and sub-spindle coordinate systems is displayed. However, as I am only using a single turret, rear turret CNC lathe, I will acknowledge this message by clicking on OK. This action now updates the work coordinate system to its new orientation as shown in the display area. The strategy is to hold this part from the previously machined outside diameter body with the chuck jaws and locate its datum from the previously machined face of turn setup 1. Select OK to confirm this new turn setup. For those of you who want to do a bit of housekeeping and have meaningful names assigned in the CAM environment instead of turn setup XX, renaming these items is just as easy as renaming them in SOLIDWORKS. For example, left-click once on turn setup 1, then I press the F2 key, or left-click once again to activate the renaming function. I will rename this to First Operation. An alternate method is to right-click this turn setup, and from the In Context menu, left-click Properties. I will rename this to Second Operation. For the second operation, I'll create a new turn feature by using the In Context menu for an OD feature with a rough finish strategy. As mentioned earlier, I'm taking advantage of using Windows box selection to select the profile geometry and have it populate within the Selected Entities group box. The last machinable feature that I'm creating is an ID feature with a thread strategy. This will machine the SOLIDWORKS 5/8-11 UNC threaded hole wizard feature of the part. Although I had interactively specified a thread strategy, it is missing critical pieces of information, which is the thread size and what type of cutting tool is to be used. By right-clicking ID Feature 3 to activate its in-context menu, select Parameters to view its ID Profile Parameters page. From the Thread Parameters method area, choices such as tap rolling, tap cutting, and threading can be selected. With this application, using tap cutting will be sufficient, and then click on the Library button. This activates an extensive tools database tap inches page for which you can choose the appropriate thread type of 5/811 UNC. Select OK twice to confirm setting changes and return back to the CAM feature tree. The next step is to generate operation plan for all interactive machinable features by right-clicking on Second Operation, and from the cascading menu select Generate Operation Plan. After some flashing and dashing, the CAM operation tree is now active, along with the second operation, as well as the relevant operation plans from its machinable features underneath in blue. To actively view and edit the definition of our toolpaths for the second operation, the next step is to generate toolpath, as this will convert all of our operation plans from blue to black text color. As we had seen in the first operation, or turn setup 1, clearing the various warning markers for cutting tools being used from the technology database and not from the assigned tool crib is accomplished by right-clicking on the operation plan with the warning marker, navigate to What's Wrong, then select Clear to acknowledge the message. The same process is repeated for the other operation plans as well. Before verifying all toolpaths using Step Through and Simulate Toolpath, adjustments are required for the second operation within the Operations Setup Parameters page. First on the list is modifying the second operation work coordinate value to 55 on the Offset tab. Second, I'd like to make changes on the chuck fixture location tab to accurately represent graphically the new chuck fixture location and how it's holding the machined part for the second operation. For clamping diameter X, I will select the outside diameter of this machined face from the first operation. The triangle display marker and the chuck fixture jaws will update to its new position in the display area. For clamping location Z, I will select this machined face from the first operation. The triangle display marker and the chuck itself will update to its new position in the display area. For those of you who want to increase the triangle display marker size from its default value, changes can be done in this field. Select OK to confirm these settings, then verify in the display area that everything is correct. The toolpath verification process is accomplished in two different ways. The first method is known as step-through toolpath. This function can be used to see all toolpaths from the top-level CAMNC manager, the individual turn setup, or each individual operation plan. For this video, I'd like to see all toolpaths for both turn setups or first and second operations. So it's a matter of right-clicking the top-level CAMNC manager, then left-click Step-Through Toolpath. The Step-Through Toolpath Property Manager gives you the ability to single-step forward, backward, control playback speed, and play forward step-through toolpath motion. Various display settings for the tool itself and its corresponding holder can be turned on or off. Information such as rapid and feed rate movement, spindle RPM, the name of the operation and the cutting tool used, as well as estimated machine time based on applied feed and speed calculations, are listed from the Property Manager. During playback, work coordinate system values G54 and G55 and the corresponding chuck fixture display for each turn setup is shown as well. Once done viewing, select the green check mark to exit Step Through Toolpath. Similar to Step Through Toolpath, the settings and parameters for Simulate Toolpath allows viewing the graphical representation of stock material removal in relation to the part to verify each or all machining operations. Once again, I'd like to see all toolpaths for both turn setups or operations. So it's a matter of right-clicking the top-level CAMNC Manager, then left-click Simulate Toolpath. The Simulate Toolpath Property Manager gives you the ability to control playback speed by this nifty slider bar, as well as single step forward, backward, and run the toolpath motion. Various display settings for the tool itself and its corresponding holder can be turned on or off, along with the ability to control collision detection and notification for the tool and the tool holder itself. A collision is any interference of the tool with the chuck fixture. For the tool holder, a collision is defined as interference with the stock or the chuck fixture. Once Simulate Toolpath is completed, to help visually simplify the finished part in the display area, I will turn off chuck fixture display. In some cases, the cutting tool created loose stock chips or remnant material in the display area. To address this, the Select Chips and press the Ctrl D key button is used. Simply click this button first, then graphically pick the loose stock chip to remove. As each chip is selected, its color changes. When all the chips are selected, press the Ctrl D key on the keyboard to remove the chips from the display area. To turn off this function, click on Select Chips and press the Ctrl D key button once again, as the next step is to show difference between the machined part and the design part. The simulation shows a graphical comparison of the two items. The amount of deviation is identified by different colors on the simulated model. Any shade of the blue colors indicates presence of material. The color green indicates the part is machined to final size or net size. And any of the warm colors, yellow through red, means that overcutting is done on the part. Since our part has ID features, click on Section View Full, and from the pull-down menu, select 3/4. This cool function allows us to view internal features of the part. All of my machinable features are present, with no collisions detected. Select the green checkmark to exit Simulate Toolpath. We're actually almost done, as post-processing and reviewing the actual NC code is the final step. As I want to post-process NC code for all operations, by right-clicking on the top-level CAMNC Manager, then left-clicking on Post-Process, this will give the results needed. Next, I'll give the file a meaningful name and its path location. Property Manager for Post-Process allows parsing of generated operation plans and toolpaths into NC code by stepping, line by line, play, or fast forward using the selected default OS ST20 post-processor. Select the green checkmark for OK to complete this function. And here's our NC code. As you highlight each line, we can see various information that is going to be used when this NC program is loaded into our CNC lathe. The caveat is that you will need to review this NC code and perform any necessary edit changes so it is safely compatible for your application. So, let's take a quick review at the entire workflow of generating NC code using SOLIDWORKS CAM Professional and CAMWorks Interactive Feature Recognition. First is the creation, placement, and usage of a mandatory SOLIDWORKS coordinate system feature. Next, define the parameters of the machine environment, especially the assignment of the main spindle work coordinate system. Specify the material type, shape, and size within the stock manager. Planning how the part is to be programmed and machined. This involves creating turn setups and determining which machinable turn features are to be used by way of interactive feature recognition. Another technique that you can do is a combination of automatic feature recognition and interactive feature recognition. Generate operation plans from valid machinable turn features, then generate toolpath to see how each cutting tool is used for that specific operation. We will check our toolpath by using step-through toolpath and simulate toolpath. And finally, post-process. Review and, if necessary, edit our NC code. And that is a detailed look at how easy it is using interactive feature recognition in SOLIDWORKS CAM Professional and CAMWorks two-axis turning. I want to say a big thanks to everyone for watching this entire video, and if you find this of value, consider giving this video a thumbs up and leave us a comment below, as we would like to hear from you. If you have not done so already, smash that subscribe button for future notifications of other entertaining content from GoEngineer. Visit our website, goengineer.com, for access to professional training and services, upcoming events, and more from your #1 online technical resource. Thanks for watching.